Good afternoon. All right. Any question before we start? So last week we started compound pendulum. So today I'm gonna finish that. Then I'll go over fully spring system to find the equivalent stiffness for those systems. We go over some examples on some class activities. So in compound pendulum, we have a rigid body which is rotated oscillates about 1 point, which we call center of rotation, and we would like to derive the equation of motion for that. So we have a rigid body like this with the center of gravity located at point G, and we would like to first derive the equation of motion. When you move this rigid body from the relaxed point by the angle of theta naught and then release that, it's going to start oscillating about point O, which is the center of rotation. We did for the simple pendulum. When we have concentrated mass, which is located at the distance of L, we could derive the equation of motion for this. And omega n, it's gonna be G over L square root of G over L. For this, it's gonna be J naught theta double naught plus mgd theta equals to 0. Omega n would be a square root of mg d divided by J naught, which is polar momentum inertia with respect to axis of rotation, which is axis O. So if I want to find if I have a concentrated mass located at the distance of R from the center of rotation, or if I ask you what would be the mass moment of inertia for this mass, JO would be mR squared. Polar moment of inertia for concentrated mass at the distance of R is going to be J naught mR squared. So what if I want to replace this rigid body with a with a concentrated mass with the mass of m, and I'm gonna locate it at the distance such that this system is gonna have the same polar moment of inertia. So what if I would like to find this distance? So in that case, J naught should be K M squared. So K, it's gonna be the radius or this length that I should put the entire of the mass of the rigid body at that distance such that this system is gonna give me the same polar moment of inertia. We call this K as a radius of gyration. So radius of gyration is defined as a term for a concentrated mass system such that this new system is going to have the same mass moment, polar moment of inertia as the original system, which is this. This is one thing. Second thing, if I want to find mass moment of inertia with respect to center of rotation, which is O, based on theorem, access theorem, it's gonna be J with respect to G, polar moment of inertia with respect to center of gravity. So it's going to be G plus the distance between center of rotation O and center of gravity, which is G. I labeled that as a D squared. So this is going to give me GO equals to GJ plus MD, sorry, MD squared. I forgot MD squared. I can write JG as a K G squared times M, same as this, radial gyration, when we are talking about polar moment of inertia with respect to gravity, K G squared times M. Then I'm gonna replace these 3, 1, 2, and 3. JO would be K naught M squared equals to KG M squared plus M D squared. 1, 2, and 3. I cancel out M squared. One of them, and it should be my bad. It's gonna be MK not squared, not M squared. MKG squared, so it's gonna be square is going to be on the top of K. So I can cancel out all n's. So I will get K naught square will be KG square plus D square. This is the equation that I find. Then I divide this by 1D, just 1D. So I'm going to get K naught square divided by D equals to KG square divided by D plus D. So I'm gonna use this equation shortly. So I'm gonna replace this J naught with this. Natural angular frequency is gonna be mg d divided by m k naught squared. Cancel out these two. I will get g d k naught squared. So if I bring d here, I'm gonna get omega n would be s square root of g divided by k naught squared divided by d. So k naught squared divided by d. If I call it as a L naught side, omega n is gonna look like s square root of g divided by L naught. So if you compare this the angular frequency of this system with the simple pendulum, which was g over L, you can see that if I put entire of the mass of this rigid body at the distance of L naught from center of rotation, then it's gonna have the same motion as original system, which was the compound pendulum. So if I replace this compound pendulum with something like this, L naught with the mass of m, and I ask you what would be the natural angular frequency of this system, you can say omega, it's a simple pendulum, it's going to be g over L naught. Then we can say this compound pendulum can be replaced by the simple pendulum with the distance of L naught. So this guy, k naught squared divided by d is gonna give me that distance. So left side is k naught squared divided by d. Right side is gonna be d plus, if you connect point O to G and go by this distance, which is g squared divided by d, you end up to point A. So GA is k g squared divided by d. So this distance is how you can find that distance. You go by that distance from point G in this direction, you end up to point A. Point A is called center of percussion. How can we find kg? You know the mass, the polar moment of inertia with respect to center of gravity. You know the mass, you can find kg. You have the d, you can find this expression. You add it to the d, you end up to point A. So this is how you can find the location of center of percussion. Why is this important? Because it's going to tell us if I put the entire of the mass of the system on the distance of L naught, which is d plus GA, then it's gonna have the same angular frequency than the simple pendulum. So this is one specification for central percussion. The other specification for central percussion is to design purpose. So consider this hammer and this baseball bat as well. If O is the center of rotation, just when you have the hammer on your hand, center of rotation is gonna be at point O where you keep the hammer on your hand. So when you hit the object, some reaction is gonna be felt here. If you design the hammer such that center of percussion locating at the point of contact, suppose you hit the object at this point and it's going to be at the same location of center of percussion, then if it happens you don't feel any reaction at center of rotation, which is point O. So your hand doesn't feel any reaction when you hit the object. Same things for the baseball bat. If you design the bat such that you hit the ball just exactly at the center of percussion, then you don't feel any force or reaction at center of rotation, which is where you keep the bats on your hand. Good? So this is one application on the design. The other application, on the car. So suppose this car is gonna hit a bomb. So at point O, it's gonna hit the bomb. If you design the car such that center of percussion for this rigid body is located at the rear wheel, then when you hit the bomb, you are gonna feel some force here, but the person on the back, they don't feel any reaction because they are very close to the center of percussion. So if on your design of the car you follow this, then you don't see much reaction on the back side of the car. So this is another example for center of percussion that the designer are going to keep on their design. And this is because of a specification of center of percussion. When it's going to hit the force on the other side, which is the center of rotation, you don't feel anything. Or vice versa, you can replace center of rotation with the center of percussion. You will get the same result. So here it was center of percussion, point O is center of rotation. You can replace them. You can put the center of rotation here, center of percussion is going to be at point O. So we can prove that. Good? Any question about this? All right, let me work on the pulleys and spring system. Suppose we have It's a pulleys and a spring. Some of the homeworks problem are suppose we have a pulleys connected by two spring to the fixed point on the top and one mass with the weight of 2W is attached to the other side of the pulley. So we would like to replace this with equivalent stiffness and one mass. Then to do the dynamic analysis or vibration analysis of this system, we can work with the simple mass and spring. So this is the idea. But the question is what would be the K equivalent for the new system? If I'm gonna represent the motion of the pulley at this point by the X, and the motion of this spring by delta 1, and this one by delta 2. So if I draw the free body diagram, force 2W is applied on one side, on the other two sides we are gonna see the W. Good? Everybody can see why it should be W on each side, because the tension in entire of the rope should be the same, and these two forces acting on these two ropes should be same as 2W to keep this mass in a stable position. So it's going to be W, W. Now, the work done by this weight, the work, is force times distance. Force times this distance is going to be the work done by this mass. So force is 2W. The distance that the distance that this mass is covering is x. It's gonna moving by x. So 2W times x is gonna be this. On the other side, the work done by this should be the same as the work done by summation of these two. This force times its deflection, which is W delta 1, plus W times delta 2 should be the same as the work done by the other side of the pulley. So this is what we know about the pulleys. So now I can cancel out W, so it's going to be 2x equals to delta 1 plus delta 2. Delta 1 deflection would be K1 divided by W divided by K1. Force, which is W, would be deflection times stiffness. So deflection would be force divided by stiffness. Same thing. Delta 2 would be W divided by K2. I replace delta 1 and delta 2 by this one. So 2x would be W divided by K1 plus W divided by K2. On this side, 2W force would be a stiffness, which is K equivalent, times X. So X would be 2W divided by K equivalent. So 2 times X, which is 2W, divided by K equivalent, would be W divided by K1 plus W divided by K2. Any question about this? Because you are supposed to differentiate or derive the equation like this for some other combination of the pulleys and the spring. How did we get this? The work done by this side of the pulley should be the same as the work done by the other side. Work is force times distance. Force times distance. This force, this weight has been moved by the x. This force has been moved by the delta 1. This force has been moved by delta 2. We could get this one. Then there is a relation between deflection, force, and stiffness. This is what we know. I replace delta 1 and delta 2 by this, and x by this, I end up to this. So we have W, I cancel out from both sides. I will get 4 over K equivalent equals to 1 over K1 plus 1 over K2. 4 divided by K equivalent, 1 over K1 plus 1 over K2, which is K1, K2, K1 plus K2. If I flip this, K equivalent would be K1, K2, 4 K1 plus K2. Any question on this? So I can replace the original system with the pulleys and the spring, with this mass and the spring system with the equivalent stiffness of K1, K2 divided by 4 K1 plus K2. And this is representing the original system. Now let me look at another example. This time I'm gonna use the energy method. There is a spring with the stiffness of K1 is connected to the pulley. K2 and mass of M has been connected to the other side of the rope. So mass, rope, spring K2, one pulley and another pulley connected, another spring connected to the pulley. So we would like to replace this with this equivalent stiffness and mass. So first thing, I assume that the mass M, the location of mass M can be represented by x. X is the displacement on mass M. So if this is the displacement on mass M, velocity of that is going to be x dot. So I'm going to use the energy method this time. Summation of potential energy plus kinetic energy of original system would be constant, because we assume that there is no air resistance, or nothing is gonna stop the motion. So we don't have any damping on the system. Potential energy plus kinetic energy of the original system equals to, it's gonna be constant. We differentiate that, set it equals to 0 other side, and derive the equation of motion for this. So for this one, if this guy is moving by m, the velocity of that is going to be x dot. So the only term which has kinetic energy is this mass, because mass is the mean which can represent the kinetic energy. Kinetic energy is always half of m v squared, and v is x dot squared. How fast x is changing with time, this is x dot. This is kinetic energy. Potential energy, we have one spring here. If this is moving by x, this rope also is going to be extended by x. If this is moving by x, this is going to be extended by x. So it's going to be half of k2 x squared. But if this one is moving by x, how much this spring is going to move it? Do you remember from the pulley? Like this, if this is moving by x, for sure, the rope connected to the other side is gonna make the deflection of x the same thing as this one. But how much this rope is gonna be moving down? Do you remember? So the displacement on this side of the pulley is gonna be half of x. So if I represent the deflection of the spring K1 by y, which is the deflection of this point, with y. Y would be x over 2. Whatever is this, half of that amount, that deflection is going to be for y. You remember this for the pulleys? If you have pulley like this, if this side of the pulley is moving by x, this point is gonna move by half of the deflection on the other side. So if this is true, by moving this by deflection of x on this row, we are going to make the deflection of y on the other side. So it's going to be half of k1 y squared. And y is half of the x, it's going to be half of k2 x2 plus half of k1 x over 2 squared. Now replace this here. It's going to be half of m x dot squared plus half of k2 x2 plus half of k1 x over 2 squared. It's constant. Now I'm gonna differentiate both sides with respect to time. Half of m is right now I can no, let me differentiate it. Half of m is constant, but this is varying with time. So 2 times this times x dot times derivative of x dot with respect to time. Derivative of velocity is going to be acceleration. So it's going to be 2 times half of m x dot plus half of k2 is constant, but 2 is coming out. X, derivative of x with respect to time is going to be x dot plus if I square this, it's going to be x squared divided by 4. So I'm going to have 1 over 4, 2 times 1 over 4, 1 over 2 k1 x dot equals to 0. Derivative of x squared would be x dot times 2. 1 over 4 is coming out of the parentheses, and 1 over 2 k1 is going to be. So I have half, and not this half. I have x dot. So what is left is m x double dot plus k2 1 over 4 times k1 times x equals to 0. This is equation of motion for this system. What is the k equivalent for this? If this is the equation of motion for original system, if I want to replace with this one, the equation of motion for this one is m x double dot plus k equivalent x equals to 0. This is the same as this, so k equivalent would be k2 plus 1/4 of k1. So this is another way to find the equivalent stiffness for the system, and at the same time you can find the equation of motion for the original system. Any question? Alright, let's work on another example. We are going to do parts of the class activity. So, suppose the original system is we have this pulley spring system, spring K connected through the rope, and this pulley to this pulley and the other spring. And on the other side of the pulley we have the mass M and the spring 2K connected to that. So we would like to find equation of motion for this system. We are going to use the energy method to do that. Let me give you a hint, then I'll ask you to do some parts of this example. So first, what I'm going to do, I'm going to replace this spring, this pulley, and this spring with the equivalent stiffness, which is connected to mass M and spring 2K. And after I figure out K equivalent, I can simply write the equation of motion, the kinetic energy, potential energy for these two, and then differentiate both sides and write the equation of motion. But the part that I'm asking you to do is finding K equivalent of this part based on what we covered so far. Is that clear? We already saw one example like this in the class, so you just need to Number 17. What do you think? The other class.
I was gonna say I got called
Your
in the
name.
class and I get called
Yep.
again. You know, it's just my lucky day, right?
Yeah.
Well, I haven't quite finished it yet. I was still trying to get the distances.
What do you think? I mean, when you look at this problem, what should be the approach for that? Or which example that we did in the class, it's similar to this one?
I was trying the energy method, the one we just did previously.
Okay.
One down here and one up there.
Uh-huh.
And
You mean this one or
Yeah.
the other one? The other one that we did.
the other one we did over there.
Okay. So that's it's gonna work, but if you look at this, K1, K2 connecting to the pulleys, and we end up to this guy. Okay. This is similar to that one. We have one spring here. The other one is not exactly after this. We just have a pulley here to change the direction of motion. This pulley is not going to do anything except change the direction of the rope from going up to going down.
Okay, that's not gonna move.
So it's not going to change the dynamic, the equation. So what we can do is we can use this equation to find the equivalent stiffness of this part of the system. Is that clear? Why we can use this equation for this? You can do whatever we did here for this one, and at the end you will end up to this equation. But what I'm saying that we don't need to do that because I can see that this one is similar to this system, except we have a pulley which has changed the direction of rotation. Still, the force in this rope and this rope is going to be the same because the rope has not been changed, and the rest of the process will be the same. So K equivalent would be K1, which is K times K2, which is 5K, divided by 4 times K plus 5K. 5K squared divided by 5K plus K, 6K, 24K. 1K can be cancelled out. K equivalent would be 5K divided by 24. So now we have 5K divided by 24, 1 mass, and 2K. Work on this for 2 minutes and derive the kinetic energy and potential energy of the system. is not brand. What do you think? Let's start with the kinetic.
For the kinetic energy, I think it would be 1/2 x naught squared.
Okay, what for potential energy?
I think I should pop one for the potential.
Okay, but I made a mistake here and nobody could catch this. When I drive this K equivalent, it was, if you remember, it was 4 divided by K equivalent equals to 1 K1 plus 1 over K2. I get 4 over K equivalent, K1, K2, K1 plus K2. So if I flip this, I need to get K equivalent divided by 4 equals to K1, K2, K1 plus K2. So K equivalent is going to be 4 times this, not divided by 4. So let me fix first. This 4 is coming up 6K times 4. It's going to be 20K divided by 6 or 10K divided by 3. Any idea about potential energy of the system? If this mass is moving by x, the deflection or the compression on this spring would be the same, x. So the potential energy absorbed by this spring is going to be half of stiffness times the amount of deflection x squared, which is going to be 2k x squared. Plus, if this mass is moving by x, this spring is gonna be extended by x, the same amount. So the potential energy absorbed by this spring is gonna be half of the stiffness, which is half of 10k over 3 times the amount of deflection, which is x squared. So if I add them up, okay, this is constant. Summation of potential energy plus kinetic. Now I differentiate them. This is constant. 2 is coming out to x dot double dot plus half of 2k. Derivative of x squared is going to be 2x x squared plus half of 10k over 3 2x x dot equals to 0. I cancel out x dot, I cancel out half, I cancel out 2. What is left is mx double dot plus 2k times x plus 10k over 3 times x. And this equals to 0. And this is the equation of motion for this system. Any question on this? So before I go through the next example, let me go quickly on the homework, which is due. Which is due this Wednesday. So I'm gonna go over the first problem, which is about the drivetrain. So for the drivetrain that you have work on that on first homework. Now we are gonna look at the stiffness. Let me look at the. So this is the blade. This is planetary stage. It has 3 gears. Second stage, third stage, and then the high-speed shaft connecting the gearbox to the generator. So what you did in the first homework, you could find equivalent polar moment of inertia for blades, gears in each stage with respect to the speed of blade. So now, in this homework first, I'm asking you to, the question is asking you to find first a stiffness of the shaft, the torsional stiffness. Here we have a shaft with the given dimension, another shaft here, another shaft there, and another shaft up there. 1, 2, 3, 4. What, if you remember, what was the torsional stiffness equation? Anybody remember that?
GJ over L.
GJ, exactly, GJ over L. So for each shaft, you have, they are made of the same material. So G is there. G is 8 times 10 power 10. So G is the same for all shafts. J, it's a, it has a circular cross section. So J would be pi d power 4 divided by 32. So the it has an inner diameter and outer diameter. So you have to consider that pi do 4 minus di 4 divided by 32. So each shaft has its own outer and inner diameter. You remember we had 4 shafts, 1, 2, 3, 4. So you can find, and L is given, you can find first KT for each shaft, and then since each shaft is rotating at different speed, you need to find the equivalent value. You have done this for the polar moment of inertia. You are going to do the same things for the stiffness and find the equivalent stiffness for each shaft. Good? There are problem 2.5, 2.5, 2.6, 2.7, and 2.10 besides this one. So it's a there are 5 problems. 14.
144. On the left.
Yes, 14. Yes. 1, 2, 3, 4, 5, 6 problems. 5 up there, and this one is 6. Here, if you for this homework, I provided the problem descriptions. I copied. So 2.5, 2.6, 2.10, and 2.14. So this is the police problem. You should find the stiffness for this rope, a stiffness for the other rope, and then start doing the analysis. A stiffness for the rope is AE divided by L. AE divided by L. You have covered those stuff. Just refresh. All right. Now, we have this pulley. So far, the pulleys that we had, we assume that they are massless. There is no mass. We assume there is no mass for the pulleys. So we didn't consider the kinetic energy for the pulleys. But now, the pulley has a mass, and the mass moment of inertia for the pulley is J naught. So this pulley has been connected to the stiffness of K at the outer radius of 4R, and in the inner radius of the pulley we have the mass of M connecting to that. So we would like to derive the equation of motion for this system. Even if I didn't provide by energy method, the energy method, it's going to be the easiest way to derive the equation of motion. So what we need to do is find the kinetic energy, potential energy. Add them up, it's constant. We assume that there is no damping. So we differentiate that, set it equals to 0. We are going to get the equation of motion. Kinetic energy is coming from this mass and the pulley. Pulley is rotating. If it's rotating, it's going to be half of J naught omega square. Whatever is the omega. Theta dot square. Plus if this mass is moving by x, it's going to be half of m x dot square. This is the total kinetic energy of the system. Half of mv square, half of j omega square. Potential energy is coming from only that stiffness, half of k y square. Whatever is the deflection on the spring, we call it y. It's gonna be y square. But as you see, there is a relation between theta, x, and y. R times theta, R times theta is gonna tell me how much would be the x. And R times, not R, 4R times theta is going to be y. So I can replace R theta dot equals to x naught. I can replace x naught by R theta dot here. So I'm going to have, and for y square, I'm going to replace y with 4R theta. Now you can add them up. half of J naught theta dot square plus half of N R naught theta naught square plus half of K 16 R square theta square. This is constant. Summation of these three terms is constant. Derivative with respect to time. This is constant, half of J naught 2 theta dot theta double dot plus half of M R square is constant 2 theta dot theta double dot plus half of K 16 R square 2 theta double. This is equals to 0. Cancel out half, cancel out theta dot, cancel out what else? 2. Now I'm gonna write the remaining term. J naught theta double dot plus M R square theta double dot plus 16K R square times theta. This is equals to 0. So these two, you can add them up. Sixteen KR theta KR square theta equals to 0. So this is the equation of motion. For this system, equivalent stiffness is 16K R square. If I ask you equivalent mass moment of inertia is J naught plus MR square. Any question about this exam? Alright, we continue. We are gonna start free vibration for damped system. When you add a damper to the system, how the equation of motion is gonna look like. We are gonna cover it. We are gonna start on Wednesday.